A single thread costs about 8 megabytes of stack memory and roughly 1 millisecond to create. Async tasks cost 200 bytes in 1 microsecond. So if you have 10,000 simultaneous network requests, async is 10,000 times cheaper. Here's how it works. Task A starts. It runs on the main thread, the yellow bar. After a few microseconds, it hits an await on a network call. The future isn't ready yet, so the task suspends, it saves its locals, registers a wake-up, and yields the thread. The thread is now free. The event loop picks the next ready task, task B, and runs it. Same story, B does a little work, then awaits its own I/O. The thread never sat idle. It just switched tasks at the exact moment one had nothing to do. Now task C gets a turn. 3 tasks are now in flight, only one ever holding the thread. 2 are suspended, parked on their futures, waiting for the network. The OS sees 1 thread, not 3, no kernel context switches, no extra stacks. A network response arrives for task A. The runtime fires the wake-up. A goes back onto the ready queue. The event loop runs it again from exactly the line after its await. Local variables restored. To A, nothing happened. It just kept going. The full picture. Every task progresses in tiny slices, sharing 1 thread, never blocking. Tens of thousands of tasks could fit in here. Each suspension costs about 100 nanoseconds, 3 orders of magnitude cheaper than a thread context switch. Compare to threads. 3 threads, 3 kernel stacks of 1 to 8 megabytes each. The kernel schedules them preemptively, switching costs a few microseconds and pollutes the CPU caches. For pure I/O work, all that machinery is wasted. The threads are idle most of the time anyway. But the catch, cooperative scheduling means tasks have to yield voluntarily. So what happens if one task forgets to await, runs a 100 millisecond sync computation on the main thread, perhaps from a sync library you imported by accident?